In this video, we're going to look at rational functions and rational inequalities. We're going to use the arrow notation that we did before when we talk about as x goes to infinity, the function goes to, that's the arrow notation. We're going to solve applied problems using rational functions. We're going to find the domains and ranges of rational functions. We're going to identify horizontal and vertical asymptotes. We're going to graph a rational function, and then we're going to solve rational inequalities. So here's some questions to ponder. The first question is, can you find more than one polynomial function for the same graph with the same zeros? And the answer is no. So each polynomial function has a unique graph. We can have a graph with the same zeros as another graph with the same zeros, but they're not going to have the same exact graph. As an example, if I tell you that f of x is equal to x minus 1, the quantity squared, x plus 2, and you go out and graph that in your favorite graphing utility, then if I asked you to graph g of x is equal to x minus 1, the quantity squared, x plus 2, but I put a negative out front, so in that instance, the g of x is not going to be the exact same graph as the f of x. So they can have the same zeros, but they won't have the same graph. Each polynomial function's graph is unique to that polynomial function. Any kind of multiplier that you may put out front of the factors, or in other words, change the leading coefficient, then what will happen is that you're going to produce another unique graph for that polynomial, but they can have the same zeros, however. Second question, how would I solve this? Well, if you were in algebra 1 or 2 in high school, what you would have been told to do is multiply both sides by the common denominator. In this case happens to be x squared minus 1, x squared minus 1, and that would have cleared the fraction. When you do that, these clear. The left or the right hand side is still 0, so I have 3 minus x. So I set it equal to 0 and I solve, and I get 3 is equal to x. So there is my solution. Notice how the denominator, because I multiplied both sides by the common denominator, which is x squared minus 1, the denominator on the left-hand side ended up canceling itself out over here, and multiplying by 0 made that 0 anyways. So it's just the numerator that's going to give us our solution, because it's set equal to 0. When solving a polynomial function, what are you finding? When solving a rational function, what do you think you're finding? Well, when we're solving a polynomial function, say I set this thing equal to 0 and solve, I'm finding the zeros of the polynomial function. And if those zeros are real numbers, then I am finding the x-intercepts. If they're not real numbers, then I'm just finding the zeros, but I'm not actually finding the intercepts. The same thing is going to apply when we're solving a rational function. Within a rational function, what we are solving for is the zeros of the polynomial or the rational function. And if they're real numbers, then those real numbers are the x-intercepts. So if I were asked to find the domain of this function, which is, by the way, a rational function, the problem child comes with the denominator, not the numerator. I can divide any number into 0, and that's fine. What I can't have is I can't have the denominator equal to 0. So I'm going to do x squared minus x minus 12 cannot equal 0, because that's where we have an issue. So we have x minus 4, x plus 3 cannot equal 0. So x cannot equal positive 4, and x cannot equal negative 3. These are the two restrictions on the domain. So if I write my domain in set builder notation, I'd write it as curly bracket x, straight line, that means such that x cannot equal 4 or negative 3. In interval notation, I would write it making sure I pay attention to the smallest number to the largest. So negative infinity to negative 3, union between negative 3 to 4, union between 4 to infinity. Both of these are valid. This is interval notation, this is set builder. When I get to the point of finding restrictions on domains, I usually flip into set builder because it's less writing than interval notation. With that said, our homework platform, which is WebWorks, will always ask for it in interval notation. On any exam that I give you, it will be either one, whichever one you prefer. And I said that that is a rational function, so let's now define what a rational function is. A rational function is any function that can be wrote as a quotient, in other words, a division, of two polynomial functions, p and q. Now, if you remember back in the rational zeros theorem, we have p over q. So we still have a p over q, but now we're talking about polynomials p and polynomials q, and not just the coefficients of the leading coefficient and, not the coefficients of the coefficients, the factors of the leading coefficient and the factors of the constant. Now we're actually talking about polynomials, but notice it's still p over q. And we have been using, by the way, our notation, which is arrow notation. We've been using this as x approaches infinity, as x approaches negative infinity. We've done that already when we talked about power functions and the behavior of the power functions. We also talked about it as f of x approaches and as f of x approaches. Now what we're going to be doing is adding this little symbol to the top right of a number. So what this means, as x approaches some number from the left, that negative means from the left, and as x approaches some number from the right, that positive, that superscript to the right is a positive, means that I'm going to go to the right, but not actually get to a. I'm just going to get close to it. Similarly, this function is going to approach a number. So we have been using, up until now, these. All we're doing is adding this and this. So using your calculator, I want you to fill out these charts. All right, after using my calculator, if I put in negative 0.01, I get negative 40. And then I put in a negative 0.001, I get negative 400. Give or take, I rounded. And then I put in a 0.01, I get 40. I put in a 0.001, and I get 400. So as I get closer to 0, I end up getting negative magnitude-wise large, non-magnitude-wise very small numbers. So as x approaches 0 from the left, which is this part of the graph, I'm on the left of 0 if I'm negative numbers, the function itself seems to be going to negative infinity. Then as I move to the other side of 0, so I put in 0.01, and I get even closer to 0 on the right-hand side, I get 400. Again, this is rounded numbers, so it's actually a couple of decimals. It's like 399 and some decimals following. So I just did some rounding to make my life easier. So as x goes to 0 from the right-hand side, that's what that plus means, my function itself seems to be going to very large positive numbers, and so it's going to infinity. As we approach 5 from the left-hand side, these two numbers are on the left-hand side. This is close to 5. This is even closer to 5. So as we approach 5 from the left-hand side, my function seems to be going to negative infinity. And as I approach 5 from the right, so 5.1 and then 5.001, which is even closer to 5, is going to be a positive number. Now you're asking me, why can't I put in 5 and 0? Well, if I look at the fact that my denominator is x minus 5, these cannot equal 0. So my restricted domain is x, so that x cannot actually equal 0, nor can it equal positive 5. So what I'm interested in is the behavior of the graph as we get close to those numbers, 0 and 5, but I'm never going to actually be able to equal 0 and 5 because that would produce a 0 in the denominator and we can't divide by 0. So on this, they're asking me to state the domains and then using your graphing calculator, sketch the graph of the function. So the first thing I'm going to do is ignore the numerator because I don't even care if factors cancel at the moment. When I'm looking for my domain, I factor the numerator, factor the denominator, but I'm really mostly concerned about the denominator first and foremost. So we'll go ahead and factor the numerator, even though I just said a moment ago I'm not going to, but I'm going to factor it anyways, because I'm going to have to at some point, just in case we have cancellations. So I have x plus 5 and x minus 2. In the denominator, I factor out an x, leaving me x minus 2. Now I'm going to caution you. We need to, at this point, before we do any cancellations, we need to define the domain with this before any kind of simplifications with the numerator, if it does. So this is going to produce x such that x cannot equal 0 and x cannot equal 2. Now my next step is, if I can cancel stuff out, I will. And my x minus 2 cancels out, and I'm just left with x plus 5 over x. Now, what does that mean in terms of my graph? Well, if I come over here and I go out to Desmos and graph this, I got to remember this one thing right there. When I go out to Desmos or any other graphing utility, what it's not going to show is that I have a hole in the graph, not unless you put your cursor over when x is equal to 2. So when I go out and graph this, I end up with a graph that looks like this. It's gonna 1, 2, 3, 4, 5. Right here I'm gonna be crossing, so it's gonna look like that. And then I'm gonna have a graph that looks like this. But what it's not telling me is at 2, I actually have a hole in the graph. So when x is equal to 2, I have this hole right there. So let me actually make that a little bit better. I have a hole right there at x is equal to 2. But I won't see that in Desmos or in your graphing calculator unless you put your cursor on top of x equals 0, or excuse me, x equals 2. And then what it's going to show you is that there is actually undefined. So be aware that if you're using Desmos or your graphing calculator to get an idea of what these look like, it may not show you that there's an actual hole in the graph. Typically, it actually doesn't. All right, so for part B, I already have the numerator factored, so I don't have to worry about that. So now I'm going to look to see if I have nice factors of 5 that add up to negative 4. And I can't think of any. For negative, 2 factors that give me 5 are just 1 and 5, and they don't add up to negative 4, because they both either have to be positive 5 or they both have to be negative 5 for me to have a positive sign right here, and in fact they both have to be negative. So I don't have any factors that are nice integer factors, so let's throw the denominator values into the quadratic. So I end up with 4 plus or minus the square root of b squared, which is 16, minus 4 multiplied by 5. Oh, I'm going to stop at that point, is because I know that this is the discriminant, and that happens to be less than 0, so that tells me that this does not factor over the reals. Not factor over the real numbers. So what that tells me is that my domain has no restrictions. So I'm going to go back to the interval notation. Negative infinity to infinity is my domain. Set builders x such that x belongs to the real numbers. So what does the graph look like? Well, I'm going to go out to Desmos. Now this was not going to produce any holes. And it's going to look something like this. In my graph, it has a kind of a bump around 2, somewhere around 2. And it bumps up to around 2-ish. So it's going to look something like this. That's what my graph looks like, y and x. And that tells me that my domain is everything, and my range, I can look at my graph. My range for this one, I don't think it's asking me to find that. State the domains, no. But let's talk about the range because we're here anyways. Is that my range is going to be positive numbers all the way up to whatever this maximum output is. So I can see the range easily on my graph. Now let's look back at this one. Now I can see that the range is going to start at negative infinity because this is going down forever. And it's going to end at positive infinity because that's going up forever. And in fact, let me put y here and x here. But I'm not really certain what's going on here. We're going to talk about that in a moment. So let's do our last example. So for the numerator, I'm going to try to factor it. And I'm like, okay, 3 and 4 and then 11. So the numerator is going to factor into 3x and x. I'm going to make this a positive 4 and this a negative 1, so there's the factors of the numerator. The factors of the denominator are going to be x minus 2 and x plus 4. Before I do any cancellations, I do set my denominator equal to 0, and what I'm going to get from my restricted domain is x cannot equal positive 2 or negative 4. Now what I'm going to do is go ahead and do those cancellations, and I end up with just 3x minus 1 over x minus 2. I go out and graph this. Now remember what happens at negative 4, excuse me. At negative 4, we're going to have a hole in the graph, even though Desmos and my graphing calculator will not show that. I'm just going to make sure that I put a hole in the graph wherever I see negative 4. And the graph looks something like this. X and Y looks something like this. And then this one kind of looks like that, give or take. Now remember, I have to go to negative 4, 1, 2, 3, 4, and put a hole in my graph right there. Let me just erase that so you can see that there is actually a hole in my graph. So don't forget, first thing you want to do is factor. When you're finding denominators, factor, set the denominator not equal to 0. And then if you're asked to graph, then cancel or simplify. The function. If you cancel or simplify the function prior to setting your denominator equal to 0 and solving, then I should probably say and solve to find restrictions. Then you are losing some of your restrictions. Okay, now what does it say about the relationship between the domain and the vertical asymptotes? Well, the domain is either going to produce the vertical asymptotes or it's going to produce holes in the graph. So if I look at my pictures here, obviously not drawn well, is that I actually have a vertical asymptote at x is equal to 2. Not drawn on my graph, so let me redraw this a little bit nicer. I was just balling out of control there. So at x is equal to 2, I have this vertical asymptote. And when x is equal to negative 4, I ended up with a hole in the graph. So the restrictions produce, the restrictions on the domain produce vertical asymptotes or holes. So these restrictions produce vertical asymptotes. I'll just do VA for vertical asymptotes, or holes in the graph. Which then says, hey, look, a vertical asymptote of graph is a vertical line where x is equal to a, where the graph tends toward a positive or negative infinity. As the outputs approach a, we write it as this form. As x approaches a, it goes to negative infinity, and what we should be seeing is as x approaches a from the left or right. So write that in your own words so that you can remember that. There are times, however, when the function will have a removable discontinuity and not have a true vertical asymptote, and that's what we call a removable discontinuity, is what I've been calling a hole in the graph. So a removable discontinuity happens when we do the factorization and then we simplify, but before we simplify, we note any restrictions that we have, and then after we note any restrictions that we have, then we simplify, and anything that simplifies out, that restriction becomes a removable discontinuity or a hole in the graph. Now we're going to talk about the horizontal asymptotes. Now at this point, we're just going to memorize this. In Calculus 1, we'll actually prove it. But right now we're just going to say, hey, this is cool, this is great, I'm just going to memorize it, I'm going to remember what this behavior is. And worst case is, by the way, is that you can always kind of guess by putting in very large numbers in the positive infinity or very small numbers in the negative infinity. That will also give us an idea of what the graph is going to look like if you can't remember any of this. So here's our first case. Now please note I do need to change the direction of this inequality. If the degree of the numerator polynomial p of x is less than the degree of the denominator polynomial q of x, then we have a horizontal asymptote at y is equal to 0. So as an example, this degree of this polynomial is 1, the degree of this polynomial is 2. This 1 is smaller than 2, and this is what the graph looks like. I have this horizontal asymptote at y equals 0. I also picked up the vertical asymptote at x is equal to -5, and I picked up a vertical asymptote at x equals 1, and that happens right here because when I factor this denominator, I'm going to factor this into x plus 5 and x minus 1, and x plus 5 produced that, and x minus 1 produced that as vertical asymptotes. The next case is when the degree of the denominator or numerator polynomial equals the degree of the denominator polynomial q of x. The horizontal asymptote is the leading coefficient of the numerator divided by the leading coefficient of the denominator polynomial. So this case, we have this horizontal asymptote at y is equal to 3. So we end up on this example, we have this leading coefficient is 3, so a sub n is equal to 3. B sub n, which is the leading coefficient in the denominator, is 1, so we pick up that horizontal asymptote. Now note that when I factor, I get this and this as my vertical asymptotes. Now the final and last one, let me change the direction of this inequality, is when the degree of the numerator is larger than the degree of the denominator polynomial. Then we're going to have slant asymptotes, or oblique asymptotes is what they're called, because they sometimes can actually be quadratic shapes. They can be cubic shapes. They're just not going to be horizontal shapes. Here's an example in which I have 3x squared minus 2x plus 1, and I have x minus 1. This is what the asymptote looks like. It is 3x minus 1, and I only pick up this one horizontal asymptote, or excuse me, vertical asymptote from this factor right here. And before we move on, I'm going to show you where this oblique, or in this case slant asymptote, came from. Since the degree of the numerator is larger than the degree of the denominator, I can use either synthetic or long division. Synthetic when it's appropriate, long division when synthetic is not appropriate. So I'm going to use synthetic division. So I'm going to put in 1 here. The coefficients are 3, -2, and +1. And so I do this 3, 3, -1, +1, 1, and 2. This gives me 3x plus 1. 3x plus 1, 3x plus 1, and so that's where I get that. I had to do synthetic or long division. And since I know that I have a remainder, obviously, that x minus 1 is not a factor of this numerator, but that's where how we discover and find the slant or oblique asymptotes, is we do long division or synthetic division, and I find the quotient using long division or the synthetic division, and that's what becomes the oblique or slant asymptote. So here's some steps on solving a rational inequality. Here's some steps on graphing a rational function. Now let's look at solving and then the graphing. I'm going to use a sign chart. So with the sign chart, I have 1 and x minus 5. The sign chart is used just like when we're graphing. Well, actually, it's helpful when we're graphing. It's not necessary, but it is helpful when we're graphing. But it is almost necessary, if you don't have the graph, to do the inequality part. So the first thing we want to do is make sure that we have 0 on one side of the inequality. Second thing we're going to do is make sure this is completely factored. List my factors as before. The only thing that I'm going to pick up is when x is actually equal to 5. When x is actually equal to 5, because 1 is never going to equal 0. So we set x minus 5 equal to 0, and we get x is equal to 5. This interval is from -infinity to 5, non-inclusive. This is 5 to infinity. On the left-hand side, if I choose a number, say I choose x is equal to 4, this will always be positive because 1 is always positive. This will be negative, and if I choose something over here, I'm going to choose 6. This will be positive. This region's negative, this region's positive. So to answer my inequality, since I want it less than 0, I want the negative where I'm below the x-axis. So my answer for the inequality part is from negative infinity to 5. If I have inclusive, and one of my values here, where I have x is equal to 5, comes from the denominator, it's never included. Even though I have inclusive, it's never included. So here's my answer. Do not use a bracket because x equal to 5 comes from the denominator. It's not actually part of the domain, so I'm not going to do that. Now when I'm graphing this, the first thing I want to do is factor everything, which this already is. The second thing I'm going to do is find my x-intercepts. And so if I go through this, find the horizontal and oblique asymptotes. Actually, it's factor the denominator, find the horizontal and oblique. So okay, we can do that. The denominator is already factored. My domain we just talked about is from negative infinity to 5, union from 5 to infinity. So I know that since I have a restriction in my domain, I have x is equal to 5 is the restricted domain. So my vertical asymptote is at x is equal to 5. 1, 2, 3, 4, 5. X is equal to 5. My horizontal, so that's my vertical asymptote. So my vertical asymptote is at x is equal to 5. My horizontal asymptote, this is case 1. The degree of the numerator is 0. The degree of the denominator is 1. So I have a vertical or horizontal asymptote at y is equal to 0. So I'm going to put that one there. Now, I know from my sign chart up over here, right? I know from my sign chart, let me just move over. I know from my sign chart, I expect to be below the x-axis here on the left side of 5 and above on the right side of 5. Then I'll just have to do is figure out what the behavior of the graph is. So as x goes to 5 from the left, well, as x goes to 5 from the left, we know that we're actually going to negative infinity, right? Right here says I'm going to negative infinity. So I've done my sign chart, which is going to actually tell me how x is behaving. So as x goes to 5 from the left, it's going down. As x goes to 5 from the right, my sign chart says I'm positive, so I'm going up. So here's what my graph looks like. So as x goes to, because our horizontal asymptote is 0, as x goes to negative infinity, my function is approaching 0, and I'm actually approaching 0 from below. As x approaches positive infinity, my function, because it's approaching the horizontal asymptote, is approaching 0 from the top. So there's all of my arrow notation, and here's my graph. On this example, since I don't already have it set where I have a 0 on one side of the inequality, I'm going to have to move this 2 to the other side. So I have x over x minus 5 is minus 2 is less than 0. Now I have to make this a single fraction. So this is 2 over 1. So I'm going to multiply by x minus 5 to the numerator and x minus 5 to the denominator so I can make a single fraction. Now what I have is x minus 2 multiplied by x minus 5 all over x minus 5 is less than 0. So I have x minus 2x plus 10 over x minus 5 is less than 0. So negative x plus 10 over x minus 5 is less than 0. So I'm going to do my sign chart over here. Give myself some space here. And I'm going to have negative x plus 10. I'm going to have x minus 5. This factor, negative x plus 10, is going to produce 10. And this factor, x minus 5, is going to produce 5. So the two places I'm caring about is when x is equal to 5 and when x is equal to 10. This interval is from negative infinity to positive 5. This is from 5 to 10. And this is from 10 to infinity. Choosing a value in this region, I'm going to choose 0. I put in 0 here, or it'll produce a positive number. I put in 0 here, it produces a negative number. So positive and negative, this region is negative. That means we are below the x-axis, which means since we know x is equal to 5 is going to be a, I'll note this as well, this is going to be a vertical asymptote. This produces a vertical asymptote. So at that vertical asymptote, as x approaches 5 from the left, my function is going to go to negative infinity. Even though this is not asking me to graph, it's going to help me set up the graph. Now I'm going to choose something in this region. I'm going to choose x is equal to 8. This produces positive, this produces positive, this is positive, so we are above. And as x approaches 5 from the right, the function is going to go to positive infinity. This 10 came from the numerator. If it comes from the numerator, it's actually a 0 of the polynomial. So this is a 0, which means I'm going to be crossing, since it's a real number, at 10, 0. So it won't be part of the vertical asymptotes because it's coming from the numerator. So I'm going to choose something in this region. So I'm going to say x is equal to 12. This is negative, this is positive, this is negative, so we are below. This does not affect the vertical asymptotes. It's just telling me where I'm crossing the x-axis. Now to actually answer this question, where is this thing below the x-axis? It's here and here. So I have the interval from negative infinity to 5, union from 10 to infinity. So I'm going to come over to my graph. So at 5, 1, 2, 3, 4, 5. Oh, I'm going to have to do these by twos. 2, 4, 6. So here's 5. I know I have a vertical asymptote. And I also know that the graph of this thing is going down on this side and going up on this side. Now my horizontal asymptote, because what we ended up with was negative x plus 10 over x minus 5 is my function g of x when I finally got done with the algebraic cleanup. The leading coefficient on the numerator, a sub n, is negative 1. The leading coefficient on the denominator is 1, b sub n. So negative 1 over 1 is negative 1. So I have this horizontal asymptote at y is equal to negative 1. So I know from the fact that I have the x is equal to 10, that ends up becoming a x-intercept. So 6, 8, 10. So here's my x-intercept. This is 10, 0. That comes from here. Now my graph, using my information, I'm going to come through and cross there and approach that horizontal asymptote. I'm going to come through up here and I'm going to approach that horizontal asymptote as x goes to negative infinity. So these are the things that I know. As x goes to 5 from the left, my function is going to go to negative infinity. As x approaches 5 from the right, my function is going to go to positive infinity. I have no more vertical asymptotes, so I don't have to write any more of that notation. And as x approaches negative infinity, my function is approaching negative 1. And as x approaches infinity, my function approaches negative 1. Now, you will note that I didn't put the superscript of above and below. The reason I didn't is because I don't know for certain. And here's how we can check for certain. Is I'm going to choose a large number. So I'm going to put in maybe 100 or 1,000 into my function. So I have negative 1,000 plus 10 over 1,000 minus 5. And I'm also going to put in a very small number, so I'll put in a negative 1,000. And this is why I said earlier, it doesn't matter if you memorize those certain cases, because all you have to do is put in a very large number on the left-hand side and put in a very small number on the right-hand side. Negative, negative produces a positive 1,000 plus 10, and then I have a negative 1,000 minus 5. I put this in my calculator, and I ended up with close to a negative 0.99. So that means I am above negative 1. So the positive 100 here says I'm slightly less than negative 1. So as x approaches positive infinity, I'm going to be approaching from the top of negative 1. I put in the negative 1,000 and I end up with a number slightly larger than negative 1, negative 1.005. So that tells me I'm going to approach from below. So that also confirms the graph that as x approaches positive and negative infinity, I am going to approach negative 1, in this case from below and in this case from above. Let's take a look at this example. So once again, I want to factor numerators and denominators first and foremost. So I have x plus 3. In the denominator, I'm going to factor out an x, leaving me 2x squared minus 5x minus 3 is greater than 0. Don't cancel stuff out yet, because remember, if we cancel too soon, we will lose our removable discontinuity or hole in the graph, and we will have an issue with domains. So this continues to factor into 2x, x, this is going to be negative 3, this is positive 1. So now I can talk about my domain. Yes, these cancel. So I know over here on my vertical asymptotes, I'm going to get x is equal to 3 from this. I'm going to get x is equal to negative 1/2 from this. Looking at the degrees of the polynomial, my horizontal asymptote is at y is equal to 0. I also have a hole in the graph, so a hole or a removable discontinuity happens at x is equal to 0. All right, let's come over here and build our sign chart. I have x plus 3, 2x plus 1, and I have x minus 3. So this produces negative 3, this produces negative 1/2, this produces 3. So my smallest number is when x is equal to negative 3, when x is equal to negative 1/2, and when x is equal to positive 3. So when x is equal to negative 3, this is a 0, which means that I'm going to have a x-intercept at negative 3, 0. Over here, x-intercept at negative 3, 0. This is a vertical asymptote, so vertical, not horizontal, vertical asymptote. And this also is a vertical asymptote. The intervals is from negative infinity to negative 3, negative 3 to negative 1/2, negative 1/2 to 3, and 3 to infinity. Choosing something in this region, I'm going to choose negative 5. This is negative, 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 negative below. But this doesn't tell me behavior graph other than the fact that I have a 0 here, which means I must be crossing. So I must be crossing, well, maybe. Let's actually do this one to see whether or not I'm bouncing or crossing, because guess what? Everything that held true about the zeros in polynomials are going to hold true about the zeros in rational functions. So if you end up with a numerator that has x plus 3, the quantity squared, that means at x is equal to negative 3, I would bounce. Now I see it's a linear factor. It doesn't have a power of 2, so I'm expecting to cross. Let's do the sign chart to confirm that. So let's put in x is equal to negative 2. This is positive, this is negative, this is negative, so this is above, plus, so it's above. X equals negative 1/2 is a vertical asymptote. So as x approaches negative 1/2 from the left, my function is going to be approaching positive infinity. I didn't do that here because negative 3 was a 0. Let's choose another number. Let's choose 0. Positive, positive, negative. This is a negative region, so we are below. So as x approaches negative infinity from the right, my function goes to negative infinity. And because this interval is between one vertical asymptote and the other vertical asymptote, that means the behavior of this vertical asymptote will follow this notation, or this sign. So as x approaches 3 from the left, my function is going to go to negative infinity. Now I'm finally ready to do this final and last one. So let's do x is equal to 10. This is positive, this is positive, this is positive, this is positive, so we are above. Now in terms of the graph, that tells me as x approaches 3 from the right, my function is going to go to positive infinity. Now to answer this inequality, I want to have above because I'm greater than 0. So it's going to be this interval and it's going to be this interval. So I have the interval between negative 3 and negative 1/2, union between 3 to infinity. Now let's come over here and bring all of this together. Here's y and here's x. I end up with, when I put in 0, which I can't technically put in 0, but if I were to put in 0 into the factored, and the factored is the h of x in factored and simplified is x plus 3 over 2x plus 1 and x minus 3. If I put in h of 0, which I technically cannot because it's not part of the domain, but I do need to know where the whole is. I need to know the output would be for the whole. I would get 3 over negative 3, which is negative 1. So when x is equal to 0 right here, I actually have a hole in the graph. My vertical asymptotes were at the negative 1/2. So when x is equal to negative 1/2, and at 3. 1, 2, 3. X is equal to 3. My horizontal asymptote was at y is equal to 0. So y is equal to 0. My x-intercept is at negative 3, 0. So there's my x-intercept. Now if we look at our chart from over here, as x approaches negative 1/2 from the left, it's going to be approaching positive infinity. As x approaches negative 1/2 from the left, and as x approaches x approaches negative 1/2 from the right, and as x approaches 3 from the left, that's this region right here. They're both going down to negative infinity, so negative infinity here, negative infinity here. And as x approaches 3 from the left or the right hand side, I'm going up. So the sketch of my graph is going to look like this. Go to that hole, come around and come back down. This is going to look like this. And this is going to look like this. So I did cross a horizontal asymptote there. So let's do the notation. As x approaches negative 1/2 from the left, my function is going to positive infinity. That's what my sign chart told me. As x approaches negative 1/2 from the right, my function is going to go to negative infinity. As x approaches 3 from the left, my function is going to go to negative infinity. As x approaches 3 from the right, my function is going to go to positive infinity. As x approaches, now I want to do the tails or the end behavior. As x approaches negative infinity, my graph looks like I am approaching 0 from below. And as x approaches positive infinity, it looks like my graph is telling me I'm going to approach 0 from above. And again, the way to confirm this here is do f of 1,000 and f of negative 1,000 and see whether or not it confirms that behavior. All right. So on this one, we're going to do the same kind of thing. We have to bring the fraction of 1 to the other side. So I'm going to do x minus 7, x plus 2 minus x minus 9 over x plus 3 is greater than or equal to 0. So common denominator is x plus 2 multiplied by x plus 3. So I'm going to do x plus 3 here. Numerator and denominator have a common denominator, x plus 2, x plus 2. So I'm going to get x plus 3 multiplied by x minus 7 minus x minus 9 multiplied by x plus 2 all over x plus 2, x plus 3, which is greater than or equal to 0. This is going to be a long one. Yay! So we're going to go ahead and multiply the numerator through, and so I'm going to get x squared minus 4x, and then minus 21, and then minus, multiplying the second grouping, I'm going to get x squared minus 7x minus 18, all over x plus 2, x plus 3, and this is greater than or equal to 0. So the numerator cleans up and we get x's cancel. Oh, x squares cancel. That's nice because if I do x squared minus 4x minus 21, pulling that negative through, I'm going to get negative, positive x squared becomes a negative x squared, and this becomes positive 7, and this becomes positive 18, all over x plus 2, x plus 3 is greater than or equal to 0. So I end up with x squareds canceling, and I end up with positive 3x, and I have a negative 3, x plus 2, x plus 3 is greater than or equal to 0. Factoring out a 3, x minus 1, x plus 2, x plus 3 is greater than or equal to 0. Now I'm ready to do my sign chart. 3, x minus 1, x plus 2, and x plus 3. Now this 3, because it is positive, isn't necessarily needed in the sign chart, but I'm going to include it anyway for consistency purposes. This produces x is equal to 0. This produces x is equal to negative 2, and this produces x is equal to negative 3. X is equal to negative 3, and because it's from the denominator, this is going to be a vertical asymptote. X is equal to negative 2, which is from the denominator, that's going to produce a negative asymptote. And x is equal to 1 from its the numerator is going to give me a 0, which gives me the x-intercept 1, 0. This interval is from negative infinity to negative 3 to negative 2, negative 2 to 1, and 1 to infinity. I'm going to choose a number in this region, so I'm going to choose negative 10. Since it's positive 3, it's going to be positive all the way through. I'm going to put a negative 10. This is negative, 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 so we are below. This tells me as x approaches negative 3 from the left, my function is going to go to negative infinity. Choose something in this region, negative 2.5. This is negative, this is negative, this is positive, so we are above. Since I have a vertical asymptote on one side and the other, both vertical asymptotes in this region will approach the same direction. As x approaches negative 3 from the right, my function is going to go to positive infinity. Simultaneously, as x approaches negative 2 from the left, my function is going to go to positive infinity. So I'm going to put in a region number in this region. Let's put in 0. So this is negative, this is positive, this is positive, this is negative. So we are below. This is a 0, but this is a vertical asymptote. So as x approaches negative 2 from the right, f of x is going to go to negative infinity. Let's put in something in this region. Let's put in 5. This will be positive, 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 so we're positive, so we are above. This is not X equals 1 is not a vertical asymptote, so I don't have to worry about this behavior of graph there. All right, now let's answer the question. We want the function that is greater than or equal to 0. So we want above. But we also have equalities. So this one does not produce an equality. So because this is a vertical asymptote, this region between -3 and -2 is above, but -3 nor -2 is included in the solution. So the solution is -3 to -2, but these are parentheses because -3 and -2 are common from the denominator and they are never included because there are restrictions in the domain. Union. And then at 1, which is a 0, I get to include it. So in this part of inequalities, even though we have greater than or equal to, if those values come from the denominator, they are not going to have brackets, they're going to have parentheses. Now, let's bring this together on this graph. So the vertical asymptotes we know are x is equal to -2 and x is equal to -3. When we got done with our cleanup, we ended up with a degree of the numerator being 1 and the degree of the denominator being 2. So our horizontal asymptote happens at y is equal to 0. We also have an x-intercept. So my x-intercept happens at, according to this, at the numerator, which is 1. So my x-intercept happened at 1, 0. We didn't find a y-intercept, so let's find that now. I ended up, when I got done, 3x minus 1 over x plus 2 and x plus 3. If I put in 0, so f of 0, this is f of x. F of 0 is going to give me -3 in the numerator, and it's going to give me 6 in the denominator. So I'm going to cross at -1/2. So my y-intercept is 0, -1/2. Okay, so here's my graph. Here's y. Here's x. And I have a vertical asymptote at -2. I have a vertical asymptote at -3. I have x-intercept at 1, 0. I have a y-intercept at 0, -1/2. I have a horizontal asymptote at y is equal to 0. My behavior of the graph, if I come back over here, is as x approaches -3 from the left, I'm going negative. So this region is negative. This region on this side is positive. This region on this side is positive. This region was negative, I believe. So this is what my graph is going to look like. I'm going to come up here, cross, cross, and approach. This is going to have some kind of shape that looks like a U, and this is going to look like that. So again, as x approaches -3 from the left, my function is going to -infinity. As x approaches -3 from the right, my function is going to +infinity. As x approaches -2 from the left, my function is going to +infinity. As x approaches -2 from the right, my function is going to -infinity. Based on my graph, I have as x goes to -infinity, my function looks like, and since I have no other x-intercepts, my function is going to go approach 0 from below. As x approaches +infinity, my function is going to approach 0 from above because I have no other x-intercepts. So there's my graph, there's my notation, and I can tell you what, this sign chart, so super helpful, not just to solve the polynomial inequality, but also to help us graph. If you are giving the graph of a rational function, what we want to do then is figure out what the rational function is based on that graph. Here's the steps. So if I'm asked to find a graph or find a function that matches this, First thing I'm going to note is that at x equals -2, I have a vertical asymptote, and as x is equal to +4, I have a vertical asymptote. So those are my denominator numbers. So x is equal to -2 produces x plus 2. And as x approaches, or a vertical asymptote of 4, would have been the factor of x minus 4. Now my numerator, because I am crossing at, or I'm actually bouncing at 2, then we know the multiplicity of the numerator, which is going to produce x minus 2, has to be a multiplicity of 2. So this is what I think my function is. This is the way I can tell whether or not this actually is my function, is I can do a test point. So let's test to see if I put in 0, if I actually get that value. So if I put in 0 right here, this is going to produce a +2. This is going to produce a +2. This is going to produce a -4. Oh, no, that's not going to produce that. So again, if I do f of 0, this is what I think it is. I'm going to get +4 in the numerator, 2 multiplied by -4. I end up with 4 over -8, which is a -1/2. I'm not crossing at -1/2. What does that mean? Well, that means the multiplicities of one of these has to be bumped up, because I'm not crossing at -1/2. I'm crossing at a positive number. So it is likely, since I'm crossing at a positive number, if I make this a power of 2, because this is a problem when I put in 0, is where the multiplicity is going to happen right here. And also, had I not changed the multiplicity of this to 2, I would have had a degree in the numerator of 1 and a degree of the denominator of 1, or excuse me, 2. The degree of the numerator would have been 2, the degree of the denominator would have been 2, which means I would have had a horizontal asymptote at the coefficients over each other, which in this case would have been 1. And I don't have that. I actually have it right here. So here is my polynomial. Let's take a look at my next one. I have x is equal to, looks like -3, and x is equal to 2 is my vertical asymptotes. So what I think is x plus 3 and x minus 2 for my denominator. Looks like I am at 1 right here, and I'm bouncing, so I think I have x minus 1. I'm bouncing. And check this out. I have this graph that looks like I should be passing -1/2. So -1/2. Let me erase this, because that should be x plus 2. X minus 2, I mean. So this is what I think my graph is. I'm going to call this f of x. I'm going to confirm this. I'm going to put in 0. F of 0, I'm going to get 1 in the numerator. I'm going to get 3 and -2 in the denominator. So that looks like it's working out. But here's the problem. The degree of this polynomial in the numerator is 2. The degree of this polynomial in the denominator is 2. So one of these has to be bumped up, because it looks like I have a horizontal asymptote at y equals 0, not at y is equal to 1. So either I have x minus 2 is squared, or I'm going to have x plus 3 is squared. Now I'm going to look at the behavior of the graph. Notice how on 2, I'm going in the same direction, and all the rest of them, when I had a singular power, they were going in opposite directions. So I think it's going to be this one. However, when I check this, when I go ahead and put in 0 now, what am I going to get? Well, I'm going to have, when I check this for f of 0, I'm going to get a +1 in the numerator. I'm going to get a positive 3 in the denominator, and I'm going to get a +4 in the denominator. I get 1 over 12. This clearly is not 1 over 12. This is the one that gets bumped up to a power of 2, but this is not 1/12. Okay, so how do we do this? Well, rather than doing a guessing, let's let this thing equal. Let's put an a right here, just like we did with our polynomials. Let's let this equal. It looks like it's crossing at -1/2. -1/2 is equal to a x minus 1 squared over Oh, actually, because I have 0 here, let's put in our 0. Over 0, 0, and I put a. 0 plus 3. 0 plus 3. 0 minus 2, the quantity squared. So I get negative 1/2 is equal to a in the numerator, because it's negative 1 squared, and 12 in the denominator. Solving for a, I get a is equal to negative 6. So I'm going to come back over here, and I'm going to put in negative 6. Negative 6. So this is my polynomial. All right, here is an example. A large mixing tank contains 200 gallons of water in which 10 pounds of sugar have been mixed. A tap will open, pouring 10 gallons of water per minute into the tank. At the same time, sugar is poured out of the tank at a rate of 3 pounds per minute. Find the concentration in pounds per gallon of the sugar in the tank after t minutes. So the first thing we want to do is, let's do S for sugar. Sugar at time t is going to be our function. When t is equal to 0, the sugar concentration is 10 at that very moment. Now, the volume of the tank is going to be V of t, so volume. This is the sugar. The volume at time t, V of t, is going to be 200, which is the initial volume, so V of 0, let's start with that. V of 0 is 200. So the volume at some time is going to be 200 plus the fact that I am adding 10 gallons at each time t. So the sugar at any given time, S of t, is going to be the 10 gallons, or 10 pounds, plus the 3 pounds per addition. So the concentration of sugar we're going to call F of t is going to be the amount of sugar I have at any given time divided by the volume at any given time, because it is pounds per gallon, because it's pounds per gallon. And my answer is the 10 pounds that I started out with plus 3 of t over the 200 gallons that I have plus the 10 gallons that I have at some given time. And that's my answer. So for us to find a rational inequality for the solution set, and this is a typo, that should be negative 5. From negative infinity to negative 5, from negative 1 to 0, and from 1 to infinity. We're going to pay attention to the fact that this has a parenthesis that tells me that I have a vertical asymptote at x is equal to negative 5. This has a parenthesis, so I have a vertical asymptote at x is equal to negative 1. This has a bracket, and this has a bracket that tells me I have an intercept at 0, 0, and I have an intercept at 1, 0. So that tells me my numerator and denominator, at least to begin with. So I'm going to have x and x minus 1, because those are my intercepts, so my zeros would have been 0 and 1, which means my factors in the numerator would have been x and x minus 1. The denominator gives me my vertical asymptote, so this must be x plus 5, and this must be x minus 1. And so my solution, due to the fact that I am below, so my graph, if I were to think about this, my graph would be, I could have below between negative 5 and negative 1. So I could be below here, above here, between negative 1 and 0. I could be below. And then I'm going to have positive 1. Positive 1 because this could be above and this could be below. So this could be either greater than or equal to 0, or it could be less than or equal to 0. And how am I going to decide? Well, I'm going to go ahead and do a sign chart for what I have here, which is x, x minus 1, x plus 5, x plus 1. Sign charts are your new best friend. So we have -5, which is a vertical asymptote. We have 1, excuse me, -1. -1? Yeah, so this needs to be a plus. So we have -1, which is a vertical asymptote. We have 0, and we have 1. So let's choose something in this interval. So let's choose x is equal to -6, negative, 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 so positive. And then I'm going to choose something in here. So let's choose x is equal to -4, negative, negative, positive, negative. So this region is negative. Let's choose something here. So let's choose x is equal to -1/2, negative, negative, positive, positive. This is positive. Choose something in here. X is equal to 1/2. So positive, negative, positive, positive. So that's negative. That's positive. Excuse me, that region is negative. Let's choose something over here. Let's choose 5. Positive, 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 positive. Okay. So for this solution to work, for this rational function, for this solution to work, my graph that I have is actually not this graph unless I put a negative out front here. But to make my life easy, I'm going to say, okay, that was a good guess, but not what the graph actually looks like. And say this is the solution. I'm in positive in this region, positive in this region, positive in this region, which would satisfy that. So I want where this graph is above the x-axis, so I could do that. Or I could have had a negative out front of x minus 1, which would have been the graph I erased. And then I would have said where this thing is less than or equal to 0, and that also would have satisfied this graph. I'm sorry, this inequality. Now let's take a look at my next one. This has come from the denominator, so this is a vertical asymptote. This is coming from the denominator, it's a vertical asymptote. And this is coming from the numerator, and how do I know? Because I have inclusive or non-inclusive. So I have a 0 at 3, 0. So here's what I think I have as my function. I have x minus 3, x plus 1, x minus 2. This is what I think I have as my function. So let me do the sign chart. So x minus 3, x plus 1, x minus 2. My point of interest is -1. I put 2, so that's awesome. -1, 2, and 3. So let's choose something in this region. X is equal to 0. Can't be 0. Let's do -5. Negative, 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 negative region. I'm going to have number in here. Let's choose 0. X is equal to 0. So negative, positive, negative, positive region. X is equal to 2.5, 2.5. Negative, positive, positive, negative region. X is equal to +5, positive, 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 positive. Now, I want this region and I want this region. So that looks like where I am below the x-axis. So I'd have x is less than or equal to 0. Why less than and equal to? Because I have inclusive on one of them. And that's it for this very long video.